Hi there, and we're going to do some past paper questions today. So first of all, we've got an enthalpy solution question, which is talking about the enthalpy solution of potassium hydroxide. It's saying that the student added 3.6 grams of the solid to the water in a polystyrene cup and measured a temperature rise. This tells you it's exothermic. It also says this calculated that the heat energy produced in the reaction was 3.5 kilojoules. We can use this information to work out the enthalpy of solution because we need to work out for 1 mole. So let's set up our calculation. We know we've got 3.6 grams and that gives out 3.5 kilojoules. And we know that's negative because it's exothermic. That doesn't really look like a 3, trust me it is. Then we need to find out this for 1 mole. Our formula mass for 1 mole is going to be this, if we work it out using the data booklet. Potassium is 39.1, oxygen is 16, and hydrogen is 1, which all adds up to 56.1. So we know that 1 mole is going to have a mass of 56.1. That means that to work that out, for 1 mole, we'd have to use a proportion, which is going to be 56.1 divided by 3.6, and we times that by the negative 3.5. When we do this, we end up with 15.583. Oops. Let's score that out. 15.583 times by 3.5, and that ends us with minus 54.54 kilojoules. And remember, this is enthalpy, so it's 1 mole, so you need to put this per mole in at the end. There we go. For those of us that are enjoying the cross multiplication, I'll do that here for you in the bottom corner. Let's go for it. So that'd be 56 or 3.6 divided by 56.1 equals 3.5 over x. That means that x is going to be 56.1 times 3.5 divided by 3.6, which gives you the same answer, which is going to be minus 54.54 kilojoules per mole. Now remember, we put that minus in because it's exothermic. There we go. So that's how to do that past paper question. Let's have a look at another one. So this looks quite complicated because it's got a diagram, but actually it's no different to what you've been doing. However, when you do read the question, it's asking for a mass in grams of calcium oxide required to raise the temperature of 210 centimetres cubed of coffee from 20 degrees to 70 degrees. Now that may be a wee bit complicated, but it's just a case of doing the kind of same thing and maybe working back the way. We would have been looking to find out the enthalpy. However, the enthalpy is already given. We're going to use that enthalpy and the energy that we would need to do that reaction, that change that they're saying here. We would use that to work out the mass that we would need to be able to dissolve to give out that heat. So let's go for this. I'm just going to do this at the side. So our energy released is going to be 4.18, and it says 210 centimetres cubed. So when we divide that by 1,000 to turn it into kilograms, it's 0.21, and then we times that by the temperature change. It's going from 20 degrees to 70, so that's a change of 50 degrees Celsius. So that's going to be, when you work that in your calculator, 43.89 kilojoules. Remember, that's negative because it's exothermic, the temperature is increasing. So that's just done the first bit. Now what we need to do is we need to work back the way. Okay, so we need to work out the mass for this energy. So we know the enthalpy change when you dissolve 1 mole. So let's start by working out the gram formula mass, because it does not tell you that. So it mentions here that it's calcium oxide which has been dissolved, and this is the gram formula mass we're going to need to calculate. So calcium oxide, if you go to your data booklet, calcium is 40.1, oxygen is 16, that adds up to 56.1, which coincidentally is the same gram formula mass as the last question. What we need to do is we need to work this out by saying that we know that 1 mole gives us the enthalpy change at the state, which is minus 65 kilojoules. We are looking to be able to make 43.89 kilojoules. So we need to work this out. I'm also going to tell you that this is 56.1 grams that we calculated there. So we're trying to work out a mass. We're going to do this a slightly different way. You're used to working out stuff on this side. We're going to use the energies instead. So we're going to turn this the other way. And to go to 43.89 kilojoules, what we're going to do is we're going to do a calculation on this side. And we're going to go 43.89 divided by 65. And we're going to times that by the 56.1. So this is new over old times other side. When we work that out, it gives us 0.675 times by 56.1, which means our mass that we need to dissolve is 37.88 grams. If you wanted to do that by your cross multiplication, I'm going to do it on this side. So you were doing 56.1 was your mass for 1 mole, divided by x is the same as 65 divided by 43.89. So when you solve that for x, you get 56.1 times by 43.89 divided by 65. Which gives you the same answer, which is 37.88 grams. Hopefully that's making sense for you there. I will just leave that here, and you might want to pause that because there's quite a lot in this slide, and just to make sure you know how to do it. That is a kind of tricky question just because it's asked in a slightly different way. It's going to be challenging the way that you would do the question. It's difficult, but once you break it down, it's not that bad. Okay, this is a wee bond enthalpy one. We're just going to work through this. So it says that if you react hydrogen and fluorine, they can react explosively, and that forms hydrogen fluoride gas. We've got the equation. Now we need to use the bond enthalpy values from the data booklet to calculate the enthalpy change for this reaction. So let's work through that just now. I'm going to rewrite the equation so that I've got more space. It's H2 F2 gives us 2HF. When we split this up, this side is the bond breaking, so that's endothermic because you're putting the energy in to break them, and this is exothermic because energy is given out when they are formed. Next step is to draw out our chemical formulas. So HH, FF, those are both diatomics, and then this is H times 2. This gives you an idea of the bonds you need to break. So in total on this side, the bonds breaking, that's going to be a HH bond, and we've only got one, so that ends up being 436 kilojoules when you look in the data booklet. This one is an FF bond, we've only got one of them as well, and that is 159 when you look in the data booklet. So that gives us a total plus or endothermic energy change for the breaking of 595 kilojoules. When we do the other side, we've got two of these bonds, so if we've got a HF bond, oops. And when you look in that data booklet, it will tell you it's 570 for one of those bonds, so we'll times it by 2. And that ends up being 1140. So in total, that's negative 1140. So that's 1,140 kilojoules that have been released exothermically. So our total energy change here, or our bond enthalpies, is going to be delta H is plus 595 plus, and then because that's a minus 1 there, minus 1140. And when you do that, it's 595, take away 1140, that gives you an enthalpy change of minus 545 kilojoules per mole. And that is the answer. So hopefully that's been helpful for you this time. If you need any help, you know you can ask your teacher for a wee hand. Okay, thank you very much.